Okay, good afternoon, everybody. Quick reminder, quiz 1 is due on this Friday. If you haven't attempted it now, quite a few people have. I've heard some good feedback on it. Some people have emailed me with questions. I apologize that I am not going to answer questions by email on quiz 1 until after quiz 1. But please do feel free to discuss different points. But no, I can't openly address questions directly on that. Other things. So last time, we introduced you guys to the last part of the Horner-Wadsworth-Emmons reaction. Remember, this is the other part of the Wittig, or the olefination chemistry. We introduced enols and enolates. These are molecules that are related to the keto or enol for the carbonyl, except we're replacing the carbon-oxygen double bond with a carbon-carbon double bond. Enols and enolates are special because what we're doing is we're addressing what we call the alpha carbons, the hydrogen or the carbons immediately adjacent to the carbonyl, and we're deprotonating, removing those protons to give you this carbon-carbon bonding characteristic. Enols, remember, are also tautomers of my keto form. These are equilibria because you have to physically remove a proton from the alpha center and you're giving it to the oxygen. Enolates, the negative charge, these are specially stabilized because of resonance. So we're talking about two different pieces on this. The stability that we get from enolates is because of resonance, and there's resonance isomers that we can talk about that. Keto-enol tautomerism is talking about moving protons around, but it's all about this centers. Now, draw the major organic product based on this reaction. So given these components, the reagents that you have, what do you think the product is going to be? Okay, as one quick part, high level, let's do some bucketing. What kind of reaction do you think you're doing here? So if you imagine, the way I like to study through this part is I go through and I look at the reactions we've been talking about, the functional groups we have. You sort of categorize or drop them into a class or a category of reaction based on the reagents you've got. This is what kind of reaction? It is a HWE. Generically, it's what? Is this an imine formation, acetal formation? We have a general category of reactions that make carbon-carbon double bonds. We call it, this is an olefination reaction. So if you imagine, the way I categorize this stuff in my head is, step 1, it's in the bucket of olefination. I'm making carbon-carbon double bonds. That's my first clue. Next, underneath that, what kind of olefination is? This is an HWE. So you've got two ranks that you've gone through. Why do you know it's HWE? Why are you putting it in that bucket? Be more specific. The answer was it has two groups on either side to support the thing. Okay, draw my eye. The what? Yeah. The nucleophile, containing the phosphorus, has two resonance stabilizing groups that once I treat it with a base, I will create a carbanion, which is thus stabilized across that whole system. Yes, those are the features that, again, we're focusing on the nucleophile. Remember, all that decision was primarily done with the stuff over the arrow, not my substrate. I didn't have to focus on that part. It's only the reagents that helps me in that category. Good. Okay, now you've got that clue. What's the second step? So 1, that's your HWE garbage. Got you. It's an olefination, making carbon-carbon double bond. We can go and do that. What's the second step? Yeah. Oh, okay, you're talking about what do I have to determine. So I just said this is my nucleophile. Electrophile, what's the electrophile over here, by the way? The aldehyde, yep, there's your aldehyde center. So it's going to be nucleophile to electrophile. That's good. What I meant was, why are you doing this?
Is it to hydrolyze the acetal?
Yes. So it can be, you could just say workup. Workup is the stuff that happens at the end of the reaction. But I'm adding this one specifically because these are conditions you've seen before. I'm adding an acid, and not just an acid, super spicy acid, right? This is a special acid we've gone. If I was just working this up, this is where, if I have way too much money, this is what I'm going to use for workup. If you're going to actually specify a certain acid that's not HCl, sulfuric acid, if it's as a sort of a leading point, if you see in a procedure where somebody is not just saying acid but TFA, there's a reason for that. And that's where those are clues for you to stop and say something about that matters. Water TFA are conditions we used for acetal hydrolysis. That was a hydrolytic method we can use for acid formations, right? So that's one piece to pick up is here. There are actually two reactions baked into this system, right? We've got the olefination. Second step could be considered workup. And if I'm adding something special like TFA, if I give you a prompt or something that says there are two chemical steps, the thing I want you to draw your eye to is there are more than just the sort of the single olefination. Don't just trip up on that single reaction. Step back to all the chemistries we have. There may be other steps we do. This is where we start to move into synthesis. Okay, so there's two different parts we're going to go through. Let's take the first one. We said carbanion will attack that center. And I'm going to draw that intermediate. Whenever you're doing this part, first thing we're going to do is redraw the molecule where nothing else has changed. So I am doing a reaction at the aldehyde center, which means the rest of this is coming along for the ride. So I still have my acetal, and this is after step one specifically is what I'm focusing on. I've got this center, still got this center. Nothing about the relative stereochemistry is going to change. Anything that was R and S, we're not doing chemistry at those centers, they're just coming along. So this part of the molecule should be unchanged. Now I've got my carbonyl center, this one here. If we don't do the full mechanism, I'm going to warp speed all the way through it. It's going to be a nucleophilic addition. You're going to get your betaine-like structure. You get your oxophosphatine-like structure. It goes through the elimination. After that's all done, we said this is a alkene. So the alkene is going to replace the carbon-oxygen double bond. Okay, last step. What goes where? I have to bring other pieces to the system. My starting material, this nucleophile contained, you can think of it as the phosphorus bit. That's job is to make that carbon-oxygen or carbon-carbon double bond. The rest of it, you can think of this as the payload. It's the stuff coming along with that central carbon. So here, the payload is this ester, this ethyl ester. There's one more atom on this center that I don't have drawn in that will be part of the product. What's missing or what's not currently drawn over there? That carbon in the middle contains a phosphorus, a carbon, and initially, how many protons? And then when the reaction's done, you're going to have one proton coming through. The last step here is you've got this hydrogen as part of your payload. That's the pieces that are coming through. Now, like you said, the geometry is going to matter. I have a double bond here where I'm going to have X and Y. I have two different things that are going to be coming into that space. So this is where, looking at your nucleophile, the phosphorus bit is gone. That is there to make my elimination happen. The two pieces are my hydrogen and the ester. So which goes where? Ester is going to be where? Y or X? Who's on team Y? Who's on team X? Y. You're right. Oh no, that was terrible. That was not planned, but funny. I agree. Hydrogen is going to go here. That means the ester chunk, so that's where you draw this part out, carbonyl OET, is going to be here. Rationale. Yeah?
HWE reactions are reversible, so it can go through the...
Exactly. The HWE nucleophile is stabilized. The addition is reversible. Because of that, the initially least favored nucleophilic attack, that's your patty cake this way, carbonyls opposite each other, the carbon phosphorus and carbon oxygen are your fingers opposite each other. Your thumbs will be on the same side so that when it goes through that elimination, they end up on opposite sides. And we're talking about the bulk, not CIP rules. We're saying that size is going to put them opposite. So this is my large group on this side. This is my, this is my large group on that side. So what I'm doing is I'm forming an alkene generally with big and big as a trans sort of just disposition. So that gives me my double bond geometry. Good. All right, that's after step 1. That would be the product after just the olefination. Let's go do the hydrolysis now. If I treat that my molecule I've just made with water and TFA, what's going to happen? You're going to hydrolyze what functional group? Is it an acetal or a ketal? This guy right here. Yeah, acetal because there's a hydrogen there, right? That is an aldehyde functional group, which means I'm going to lose this chunk right here. That carbon, the one that's attached to 2 oxygens, that's the masked carbonyl. That is the aldehyde that I'm sort of hiding up right now. That's what gives it the acetal name. So when I do that, I'm going to be clipping this bond and this bond, which means everything above and below those lines, that's just the payload that's coming along with this reaction. Nothing else is going to happen in terms of relative stereochemistry. So after I do the hydrolysis, I'm going to redraw the carbon skeleton down here, double bond, O-ethyl, right? When I do this hydrolysis, that acetal, this oxygen becomes what functional group? Acetal there, this center becomes what? Alcohol. That's right. OH. What about the other center? This one becomes alcohol too. Yep. The chunk in the middle, this piece here, that's your aldehyde piece. So that would just be acetaldehyde, CH3H. That's the 2 fragments. Again, usually we're going to focus on that part here. But most important, the geometry of the double bond, that's set by your HWE. Next, the relative stereochemistry at your alcohols is not impacted by this reaction. The hydrolysis is fracturing the carbon-oxygen bonds toward that acetal center, not the others. Yes? Say that one more time. How do you know? With which other, you mean with, sorry, with this double bond? Yeah, this one and this one. So the question is, how do you know it doesn't react with those two? What's a reaction you could do with those right now? Hydrolyze the alkene. So what does that reaction look like? You remember the conditions for something like that? You're right. Now we're talking this. If you protonate the alkene, and then water was to come into that oxo and then add into it, then you'd get this OH addition across that piece, right? Do you remember the conditions for that? You're usually, and again, this is where the important part, and what I'm going to focus a lot more about this year is you guys will start seeing common conditions, but we're saying, oh, here it doesn't touch it versus there it does. The key that I'm going to emphasize on is things about temperature, strength, and time. Those are your 3 reasons that you have to sort of focus through. Hydrolysis of an acetal like this is an isoelectric surface where we're using Le Chatelier, lots of water to drive in equilibrium. This is in the realm of room temperature, happens easily. That's the piece I'm giving you there. So if you look at the conditions, there's nothing about high temperature. There's nothing about forcing conditions like extra time or pressure. So the key here is if you look at these conditions, these are what we would consider gentle. Acid, water, we're done. That's a typical thing for deprotonation, is they happen under sort of more ambient conditions. That's for number 1. Hydrolysis that you're talking about for an alkene, that's like boiling phosphoric acid. So it's a whole order of magnitude more difficult to get there. Really what we're saying is, yes, it could happen, but you're going to have to push a lot harder with a lot more reagents in order to get it to happen. So that what we're targeting here is the easy reaction first, the hydrolysis, not double, right, in that case. Absolutely, yeah. Hydrolysis of an ester is also in scope, but once again, temperature, strength, and time. So this is the piece that we're going to emphasize through is each of these reactions where you're using this, they fall on a ladder of different reactivity. What you guys now know, what we've all agreed to, acetal hydrolysis is kind of bargain basement. Imine formation, very easy. Ester hydrolysis is the next one up. We'll talk about that one in the next sector of how we do manipulations at the carboxylic acid one, but that is a degree of magnitude harder than acetal breaking down. In the same way, if you guys remember, what is more reactive, a ketone or an aldehyde? And everybody says in one creepy voice, you guys know that now, that's a rank point. Same thing here, acetal is easier to hydrolyze than an ester. An ester is easier to hydrolyze than an alkene. So those are the how you know is partly look at the conditions. If you don't see a lot, if we're not giving you something like you're boiling this in acid, you take it to mean that we're doing the easy one first. Another thing too with multi-step transformations like this, if it gets really ambiguous, I'll give you the formula. And that will help to focus you guys on what you guys are working through. Make sense? Any other questions? Again, really good discussion. This is an important feature to this. Okay. So, talked about enols. Draw all of the possible enols of this molecule. Okay, let's work through this one. First, again, whenever you're dealing with a question like this, first thing you're usually going to do, I have a strategy that I really adopted when I was learning this material. When a question's given to you, instead of attacking the question, I used to have a journal that I used to keep beside me. I'd take the question and I would annotate down 3 individual things before I ran the question. This is the strategy I used to do as a study component. Step 1, I get a question like this. First thing I write down is, what is the question asking me? It seems pedantic, but it's really important to document that. Number 2, where does this question come from? What chapter? What lecture? What material? Everything I'm asking you comes from something to do with the lecture I've gone. It may seem tangential, but it's based on a content question that I've presented. So grounding it based on your assumptions is the second thing. The third thing you do is, how are you going to attack the problem? What's your strategy? What's your approach? Whatever. And again, this is something I used to do when I would study through. I would have my actual working book and then a notebook where I would populate question 1, what's the question asking? Where does it come from? What am I going to do? I would write down those notes, attempt the question, and why this matters is I could go back after. If I was wrong, I could look at it and say, I got it wrong. Why? Because it was asking me for the number of enols, and I drew every imine I could think of. I did not understand the question or the assignment. 2, where did it come from? I could look at this and say, oh, that's definitely from oxidations. Nah, man, it's from lecture 6. So you're in the wrong chapter, you started on the wrong foot. Or number 3, approach. What am I going to do to take this one on? I could look at this and go, well, I probably have to make ketones. Dude, that has nothing to do with what this question is asking you. So it allows you to sort of systematically document your approach and adjust. So let's do that here. What's the question asking me? Draw all the enols. Okay, behind the question, what else is it? Like, it's asking you about enols. In order to make an enol, what do you need? You need a carbonyl, right? And you need what next to the carbonyl? You need it's called some type of carbon. It is you need an alpha carbon and you need a carbonyl. You have to have that. So kind of what the question is kind of asking you is, how many alpha carbons do you have? Because you need an alpha carbon and a carbonyl. Now you're playing with permutations. That's number one. What's the question asking you? Where is this question from? Where did we talk about this? What lecture number? This was lecture 7, right? So that gives you a grounding. What are you going to do? Well, if you need an alpha carbon and a carbonyl, you've identified those compounds, you will then draw each of those enolizations, right? This is a strategy where you're doing permutations. Okay, let's start with the first one. How many alpha carbons do you have? There are how many? There are, okay, so clap when you hear your number. There are 5 alpha carbons. Oh, wow. There's barely 5 carbons. They're all alpha carbons. Are there 5 alpha carbons? Are there 2 alpha carbons? Are there 17 alpha carbons? You're just clapping. Thank you, thank you. 3 alpha carbons. There we go. Alpha carbons are the carbon immediately adjacent to the carbonyl. You have 3. At any point in time, to make an enol, you will borrow one of those alpha carbons. We're going to move a proton from that center, and you're going to promote it back to the oxygen. So alpha carbons is half the battle. The second half is which alpha carbons have alpha protons. Do all of them have alpha protons? Yeah? What if I did, oh man, the voice today. What if I did this? What if that was a methyl? Can I make an enolate or an enol at that center now? No, no more protons. Still alpha carbon, but cannot work. Okay, so we have 1, 2, and 3 centers. Okay, so version 1, I'm going to take, and I'm going to deprotonate there, I'm going to make a tautomer there. So if I drew like this, OH, this center, don't touch that one. Everybody agree? Favorable in scope? Yes? Cool. Is this a new one? What if I do the same thing over here? Did I just find a new one? I found the same one. Because of symmetry, right? Like the left, these two. That means that if I only deprotonate one of these, or one of these, because of that axis of symmetry, these are the same compound. So this is symmetrically related. Not good job, C+. All right, give me another option. So I can't just deprotonate this or this. Well, let's go for that guy. Agree? Please agree. Yes? Cool. Yes, a question. Yeah. Okay, fair. It has a potential enantiomer, right, between those two, left and right. But again, symmetrically, let's just leave it at, yes, you would have an R and S center because of the plane between the two. Let's go with big buckets here, right? So you're right. Along that center on there, that's not what's not R and S. What's that called? Basically, you break symmetry across this to create 2 enantiomers. We're not going to go that far. We've got these two. Any more? How? There's actually 2 more we got to find. Yeah. Oh, yeah, really? Yeah. Basically, remember, if I have multiple alpha centers, I've got enol 1 and enol 2, but I still have a carbonyl. These 2 compounds are still in play. The 2 ones I just made, what I called compound number 1, compound number 2, does compound number 1 still have an alpha proton that I could enolize? Yeah. Compound 2 has an alpha proton I could enolize. So we got another move. I could go from number 2 to make, let's leave that stuff in place, OH. And I could make this one. That's now promoting over here. From compound 1, I could make, removing that center, like that. What if I removed this center? From compound 1, if I remove this kind of light green one, what happens? What do I make? Whoop. This one. It's just symmetric. It's flip and both. So basically, I have 3 centers. I have 2 different permutations at one center. I have deprotonate or enolize one, enolize the other, and enolize both in 2 different geometries. There are 4 possible unique permutations, not including maybe enantiomers of those other points. Make sense? So how would, like if you said that these are all possible guys over here, if you had to guess, blue, fuchsia, red, green. Okay, let's give them numbers. I'm sorry, my colorblind folks. 1, 2, 3, or 4. Which is most stable, if you had to give a guess of these? Okay. So let's narrow it down. Somebody give me one as a possible. Which number do you guys want to stand behind right now? Yeah. Okay, we got 1 vote for compound 2. Cool. Anybody else? No? 3? Okay. For the opposition, compound 3. State your case.
There's a conjugated pi system.
There's a conjugated pi system, right? Everybody agrees? Conjugated pi system. Jury, do you believe your opposition? Okay, number 2. There's your challenge. Number 2, do you have a conjugated pi system? They've got a conjugated pi system. You don't? You're a terrible attorney. So, I'm sorry, counsel. They've got one too. Why is your conjugated pi system cooler than their conjugated pi system? Don't bail.
I'm just trying to think of the words.
Somebody help her out.
It's in a ring.
It's in a ring. That's a great reason. No, fair. You know, it's in a ring. Rings are cool. Not buying it. Would you like to revise your decision?
No, because now I'm looking at it, 2 might be right.
2 might be right. You're caving. That's fine. I'd probably go with 2. Well, no, but why? Give me a reason. Yeah.
The 2 has a pi bond between CNO, which is a lot.
I've got a pi bond between carbon and oxygen. The carbon-oxygen pi bond generally is going to be stable relative to the carbon-carbon pi bond. Remember, keto versus enol, just straight up. A keto versus an enol, who's better? Keto. At least if I'm going to lose one of my keto forms in favor of an enol, at least I'm going to do it for resonance, right? I get a conjugated system out of it. But if I can keep one and not the second, probably favorable, right? In that sort of case. Either way, these will all be exchangeable protons. That's the key of this, is every one of these protons in solution, at some point of the time, it's going to depart those centers. That hydrogen is not going to be fixed at those centers. They're actually going to be kind of acidic. They're going to be bouncing around. So that is going to lead us to HD exchange, hydrogen deuterium exchange. This is one way of actually experimentally measuring where these kind of centers of enolization are actually happening. And we're going to talk about oxidation and reduction. So we mentioned last time, enols and enolates. Remember in your head, oh, sorry, yeah. If you had to pick between 1 and 3, which one would win? Again, good question. What do you think? What are the rationale?
I would still say, I would say 3 probably because it has a conjugated pi system.
Yeah, if you were only given 1 versus 3, let's forget about all possible ones. If you're just asked to look at these 2 and say who is more stable, yeah, 3 at least has conjugated system. 1 has a keto but not conjugated. That's kind of the worst of both worlds, right? If you have the opportunity, it would be highly favorable to jump over to 3. But that binary comparison is exactly what you want to focus on. Look at between 2 fixed points, what are the pieces that you could potentially grab onto? Really good comment. Any others? Yeah?
Just very quick. Last lecture we were talking about the different sites and Hoffman ways you could go about
Wait. So you're saying, sorry. You're saying kinetic versus thermodynamic enolates to do which, sorry?
To do 3.
To make 3.
Because one of them is the most substituted, the other is the least substituted. So you don't have anything.
Okay, I'm going to build a question based on that. We'll play with next time. That's good. I get what you're getting at. Not what I was thinking of. You beat me there. Let's come back to that. I get what you mean, but not the point. Okay. You guys remember these. Enols and enolates. And again, the main thing about them I want to focus on is it's a deprotonation at that oxygen. You can think of it as related to alcohols and alkoxides. When we start talking about hydrogen deuterium exchange, what we're doing is we're using these acid or base conditions to find centers where enols could have existed or where enolates could have existed. We're basically saying which protons are flexible or exchangeable. So what's going to happen is I'm going to run it in a solvent that has something like D2O. Or I could use MEOD instead of methanol. Or deuterium chloride. It's the deuterium version of hydrochloric acid. Or NaOD, where again, each of these, what we have is some heteroatom X bond instead of having an OH, like an OH alcohol, what we have here is an OD or some other type of D plus type reagent. Each of these, if you look at them, we're dealing with a deuterium plus kind of component, where what we're doing is taking solvents that have these as materials based into it, where we're exchanging protons for deuterons, D plus. So what that means is I can take a system like this, and by treating it either with exchange conditions acidic, in this case D3O plus and D2O, or under basic conditions, both will give you the same answers. Like that, I want to make that clear. It's not like, oh, under acidic conditions, these will exchange. Under basic conditions, others will exchange. Remember, you have 2 different pathways to get your exchanges to happen, enolate under base or enol under acidic. So the centers that can exchange do not change because it's acidic or basic. Both can be applied. So in this guy here, back to what we said, when you're asked a question, 3 things you go through. What's the question asking you? Where did it come from? What are you going to do? So what's the question asking you here? Determine which hydrogens will undergo exchange. What's kind of the question behind the question? Louder? Which protons are exchangeable? In order to determine that, which protons are exchangeable, you need to answer how many alpha protons or alpha carbons do I have, right? You're digging in and saying, I need to form enols and enolates. Where is this information from? Right now, baby. It's from lecture 8. Cool, thank you. And what are you going to do? Find the alpha protons. So same thing. How many alpha protons or how many alpha carbons do we have in this molecule? 1. How many exchangeable protons attached to an alpha carbon are there? How many? 2. 1, 2. Why not this one? Yeah, that's the simplest one. It's not an alpha carbon. So, and I'm stating this right now. If anybody on the final exam says, oh, Jason wants to get exchangeable protons, so I'm going to exchange this one and this one and this one, I will be so, so sad. That's me crying. That's me mad. That is not an alpha proton. The hydrogen attached to that center is not acidic. In your world, there's almost no way you guys have to do that. So please, not this one. Think of it this way. If I have to exchange that center, it means I need to leave that proton as an H+. If I take that aldehyde proton and lose as H+, I make carbonyl minus. That is a very angry molecule. The pKa of that is insane. That is not an exchangeable on only these 2. So over time, you're going to exchange both, right? And this is probably what you'd observe is these 2. What if I drew the enol form of it? So let's say I'm going to draw it like this. In the enol form, where should I put my deuteriums? So first thing, there's still going to be 2 deuteriums on this molecule. Where do I go? Yeah? Yeah, number 1 is right here, because that's the same guy right here, just in a different tautomer. The second one is right there. That OH is an exchangeable center, the same way that in water, the D2O is made up of taking OH and exchanging with deuterium. So these two is the enol form of your deuterium. It's still two exchangeable protons. You're just looking at the keto and enol versions of those two centers. So we're going to go through that one. This is what you guys will try later. Go through this and actually find where these are going to be and draw where deuterium is going to happen. I'm focusing on basic conditions for this. All right, so now we're going to use these centers. Finding these protons in different places matters. This is a way to sort of tune in and say where enols or enolates could exist. It's a way of identifying centers of potential nucleophilicity, where chemistry is going to happen. We're going to start using it now where if I want to use these acidic sort of centers, I can now add other electrophiles to these systems. This is acidic bromination. This is a reaction you guys now can use. If I take bromine under acidic conditions and my ketone, these are the two products I can form. I can get a bromination at two different alpha centers. I have an alpha carbon here, which corresponds to that guy, and I've got an alpha carbon here, corresponding to this one. So what I'm showing is I actually get, and I'm giving you guys an outcome here. If you run this reaction, you make major monobromination on the interior carbon. Why? What's your rationale that follows this up? Yep.
It's the more substituted between the two alpha carbons that you create, so it follows side steps.
Right, so number one, remember, this is not going to happen in one step. You don't take this ketone, bromine, and go boom. It has to form a reactive intermediate. These are both going to come from, in this case, the major product I have here. Actually, let's color code that. This major product here came from that enol. Under acidic conditions, we can generate an enol. Once I've made my enol, that enol can undergo an addition. If it collapses down and picks up, let's say, Br, I'm using the nucleophilic character of that alpha center to capture my bromine and add to that center. Yes?
Would you ever get a bromination reaction in which you have a Br and then a Br connected
To the same center?
to the Br and O? Like how?
Oh. Wait a minute. So you mean you want to make O bromine?
No. Like,
Thank goodness. I was about to call federal security. No, what?
like when the Br has like this and then it comes in from the other side.
Sorry, I need more words. The BR, like, I can't.
To, like when you use Br2 on a normal alkene with a
Oh, you're saying, okay, you're saying I took bromine, I'm going to call this an alkene, I'm going to make a bromonium and add to, okay, similar. You can think of it the same way. The outcome's going to be the same, right? This is I'm drawing it this way, this nucleophilic cascade as a 2-electron nucleophile. That sort of draws this point. If you want to draw it as maybe, it's an alkene, I make the bromonium, and then something else comes in. That's a different reaction. It's called a haloform reaction. We'll talk about that a bit later. But this is the classic, this is a way lower energy pathway because you're using the enolate, the carbon nucleophile character, to just grab Br+, rather than sort of the bromonium one. We'll talk about that one after. So this is your standard bromine addition. The thing I want to map out is you get this one here, the major product, from the more substituted enol. So the thermodynamic enol makes a thermodynamic nucleophile to make this major product. You could generate the other one from that enol in order to get the distal center. And yeah, the distribution we're seeing here is just under acidic conditions, under equilibrium conditions, the green enol is going to be your major nucleophile, so the product, or the adding bromine to that center, is the one we're getting major. One more feature that's really important too, we only really ever add one bromine and one bromine. This is pretty easy for us to do. So if I'm trying to do a reaction like this, I have a ketone. Under acidic conditions, I will get bromine on the more substituted center because it went through the more substituted enol. And second, it really only adds once. I can surgically add a bromine to that internal center, not two. Sorry, questions on this one before we jump to base, because you'll see what I mean about two additions. Yeah. If you do this, under basic conditions, here's what we have. Now again, I've got a case here where I'm not saying left or right, more or less, but under alkaline conditions, you get addition, but more importantly, you get 2 additions very easily. It's actually really hard under basic conditions to only get 1 surgical addition. So let's look at this one. Here we don't have to choose the example I've presented. I have only 1 alpha center. I have 2 protons, and I'm actually going to color code them. So I've got 1 and 2. I've only got 1 center there. Under basic conditions, the intermediate I'm generating is going to be not an enol. Because it's basic, we're generating an enolate. And we have, cis and trans. We talked about those. Let's just assume right now that the carbon and carbon thermodynamically are going to stay furthest away from each other. The trans compound between the 2 bulky groups is usually what you're going to generate. So we get a geometry like this. And it's going to be the sodium version of that. What's happening now is that same mechanism. Oxygen collapses down. This is going to go find your electrophile and generate your Br minus. The other thing you have here is Br minus in this case. That's how you do the first addition, right? I deprotonate my alpha center. It's nucleophilic on that carbon. I add a bromine. And let's say I was just dealing with the green one. That means I'm going to leave behind that hydrogen, right? What is the change in pKa of protons here versus here? Your starting material, are those protons more acidic or less acidic than the intermediate in the middle, the monobrominated one? So who's on team more acidic here? This is more acidic. So monobrominated, more acidic. Who thinks no bromine, more acidic? Okay, those were really small hands. Think about this. What makes something acidic? If I'm ripping off a proton, I've got both cases, hydrogen, hydrogen. They're both alpha centers, which means they both, if I make a negative charge on both of those alpha centers are stabilized by the carbonyl. Those are all the same. The only difference between a negative charge, if I were to deprotonate this guy, the negative charge I make, the enolate I make, let's draw it in the other form. It's like that. Negative charge here. If I were to come from this one and I deprotonate it, if there's a hydrogen there, that's the enolate I've got. That's the carbanion I have, right? If I start from the no bromination, deprotonate it, I get a simple carbanion like this. Versus if I have a bromine here, and that's minus, which is more stable? The anion on the carbon near a bromine or an anion near a carbon just with hydrogens? Induction, right? Bromine helps, which means this proton is way more acidic. It just means this second step, deprotonating that, gets easier. You have your first example of a reaction where I have 2 protons at the starting material. I can deprotonate one to make a negative intermediate. That intermediate makes a product, and the product I make is now even more reactive to the same reaction that I started off with. If I have to deprotonate my initial starting material, one of those 2 protons come off, in scope, it can happen. But I make a product where I've now acidified the remaining proton, which means that next one is going to happen fast. It's going to be a quick reaction. It means you can't stop in between. This is like running downhill on ice. If you get over the top, once you start on that hill, you are still going all the way through. So this is where, under basic conditions, dibromination is what you will end up getting. Acidic conditions is how you do monobromination or monohalogenation. Basic conditions is how you do dibrominations or dihalogenation. Yeah?
The acidic halogenation, why didn't he get the bromination of both sides?
Like here and here? You could. You absolutely could. I think the way that we do this, generally these are slow enough that by metering in bromine, we've got a little bit more control. You'd have to do it by stoichiometry. But you're right. You could hit here and still have this problem. You're right. The same rule that we just finished talking about base, though, is why you get monobromination. Remember, if I take an electron withdrawing atom like bromine, it stabilizes anions. That's what I have for acidic systems. It also destabilizes cations. If I have a pulling on the system that's brominated, the intermediates I have under acidic conditions are all positively charged. They're going to be more unstable than the negative one. That's where we get this degree of selectivity. Make sense? Yeah? Why don't we make which? Like the bromonium bridge? This is just the relative energy levels. There's two parts to this. Remember, to bring bromine as that bromonium in there, think of it this way. What I'm showing you here is standard SN2 kind of chemistry, right? Carbon can approach a bromine and eject a bromine. That's like an SN2 reaction. The bromonium bridge, what's the ring size you have to form? You have to make a 3-membered ring. You can access it. That is basically a ring of last resort. I've given you a reaction that is possible because I've got this 1, 2, 3 centers. It acts like a carbon minus system, like a single nucleophile, rather than more like an alkene. That's number one. So it's a polarized system rather than just being a double bond. The second one is, in this reaction, I'm doing a standard SN2 where I don't have to go through a nice bridging 3-membered ring. I don't have to go to a high energy ring system. That is preferable. This is a lower energy pathway compared to having to form that 3-membered ring. Make sense? Okay. All right, guys. We'll pick up with oxidation states at the beginning of next class. See you guys on Friday.
Hey guys, okay, so we're going to do base catalyzed HD exchange. Now in this molecule, once again, identify your alpha protons and your alpha carbons. That's these two centers here. You will have 2 alpha protons on this side, 1 alpha proton over here. And if you're going to do deuterium exchange under basic conditions, remember this is a base, is going to deprotonate one of these centers. So our hydroxide might look like this. From that blue side, that's going to give us this enolate, 1 hydrogen remaining, and then in the presence of something like D2O, think of it where you've got that exchangeable proton, the exchangeable deuteron right here. So as this acts as a nucleophile, you're going to be picking off that center. So explicitly we can show this as DOD, and we're regenerating our base when we do that. So after that you will get protonation there. After 1 cycle you'll have 1 deuterium and 1 proton with this center still untouched. Now one thing I want to be to emphasize, let's imagine we keep going from here, right? If we came in this system and we keep waiting, so we still have base still present, like we just regenerated a base over here, it can now, let's say, do the second center. Now it could deprotonate the deuterium or the hydrogen. Both are still possible. It's just that, let's say that over time, on average, you only have the hydrogens from here. You have a whole solvent made up of deuterium and exchangeable deuteriums there. So yes, you still could maybe deprotonate this deuterium to go back to this intermediate, but the probability says that when it's picking up a proton, because this is our solvent, you'll eventually pick up a deuterium. So over time, both of these two centers will exchange. So the probability of removing that proton and replacing with the deuterium is higher. So after 2 cycles, you would end up with 2 deuteriums here and here. Now those are the kinetic center, right? But again, imagine if we're allowing this to happen over time, deprotonation at this remaining center is also likely. I just want to draw that out explicitly. Imagine you have your base is going to deprotonate here to give you the other enolate. As we draw that enolate, there's an important feature I want to point out. Notice the chirality. at this center now. By deprotonating this alpha center, we've gone from an sp3 center down to an sp2 center, which means it is now planar. And when it adds a proton back, or a deuterium back, so in the final part of this mechanism, this is going to add and pick up a deuterium, D+, or again, HOD in this case, which means you're going to add a deuterium from either face. There will be actually two possible products here where we will make both enantiomers at that center. So the carbonyl will be back. I will have deuterium, deuterium, and I'm going to do this by wiggly line. Redraw that again. Wiggly line deuterium, wiggly line methanol. Here, hold on. Let me slide this over just a bit, like that. So basically, we're going to end up with two possible geometries at this center, because the sp2 center here can be protonated from either the top or bottom, giving you both enantiomers at that center. So you could also draw it explicitly where we have methyl front deuterium back and deuterium front methyl back. Both are likely.